So batteries have come a long way since their invention around 200 years ago to the lithium-ion batteries we know today that powers our phones, laptops, and cars. Even so, we still have a long way to go. We need batteries to be better because batteries are key to making the transition between fossil fuels and clean energy sources. To completely rely on renewable energy, we must be able to store it for times when we don't have sun or wind. And we need the batteries to be strong, reliable, and be able to power entire cities. Today, even the most advanced batteries are not up to the challenge. Issues with capacity, lifetime, cost, and overall performance need to be addressed. So how does a battery work exactly? A battery is a device that stores chemical energy and releases it as electricity. The battery is composed of two electrodes, the negative and the positive, which are separated by an electrolyte, which is simply a salt solution. In a lithium-ion battery, we'll use a lithium salt solution. The battery operates by separating lithium ions from their electrons. The lithium ions travel through the battery, through the electrolyte, while the electrons travel through an external wire. During the charging process, the ions travel to the negative electrode, where they reunite with their electrons in a high-energy state. During the discharge, they go back to the positive electrode, where they release this energy. The movement of the ions and the electrons is coupled. They always move in the same direction and then reunite in the electrodes. But not only the lithium ions can react with the electrode. Also, the other electrolyte components can react, such as the solvent. These reactions form a surface layer called the solid electrolyte interface, or SEI. Ideally, this layer will not hinder the movement of the ions and allow them to enter the electrode, but this is not always the case. Taking a closer look inside the battery, we can see the lithium ion in three distinct environments. The dissolved lithium ion in the solution, the lithium ion that is bound to the surface layer, and the solid lithium inside the electrode. In different batteries, which have different conditions and different electrolytes, different surface layers will form. Some of these surface layers are beneficial to the battery. They allow the lithium ions to pass through into the electrode while protecting the electrode from degradation. But in some cases, a surface layer forms that hinders the battery performance. It blocks the lithium ions from entering the electrode and causes degradation to the electrode. The different surface layers, the nature of the surface layer, is extremely significant to the performance of the battery. And yet, it is the least understood component of the battery. It's not due to lack of trying to understand it. The nature of the surface layer, the random formation process, its diverse chemical environments, and this very small size compared to the other components make it very hard to study. So we need a method that will enable us to probe the different chemical environments in the battery, to help us diagnose malfunctions and defects. Just like the MRI machine is used to diagnose disease in humans, we can use nuclear magnetic resonance, or NMR, to try and diagnose our battery. In MRI, we measure the hydrogen atoms in the water molecules in our bodies. But virtually any element with a strong enough magnetic moment can be measured with NMR. So in the battery, we will measure the lithium. But let's back up and understand NMR a little bit better. So NMR measures electromagnetic signals generated by NMR-active nuclei under a strong magnetic field. In a given magnetic field, the frequency depends on the chemical environment, the frequency of the signal that we detect. The signal is generated because the nuclei behave like tiny magnets, and they align themselves in the direction of the magnetic field. For example, let's see how it works. We have here an ethanol molecule, which is actually the alcohol that we all drink in wine and beer and other drinks. We can see that the protons, or the hydrogen atoms in this molecule, belong to three distinct chemical environments, which result in three different peaks in the NMR spectrum. So as you can see, NMR is a very useful method for separating different chemical environments, and we can use it to separate the different chemical environments of lithium in our battery. So looking back at this scheme, this is a scheme of a half battery cell composed of electrolyte and only one of the electrodes, which is made of lithium metal. We can see again that the lithium belongs to three chemical environments: the dissolved lithium, the surface-bound lithium, and the lithium in the electrode, the solid lithium. So we expect to see three peaks in the NMR spectrum. But as you can clearly see, when we measure, we only have two peaks. One very sharp, intense peak for the lithium in the solution, the dissolved lithium, and one smaller peak for the lithium metal. But the peak for the surface-bound lithium is missing. There are many reasons for this, including the diverse surface layer, which has many different chemical environments, the quickly disappearing signal of the surface-bound lithium, and the very small surface area. We see the surface-bound lithium, the signal of the surface-bound lithium is hidden underneath the dominating signal of the dissolved lithium ion. So it can't be seen with a simple measurement. But we know that these environments are always in exchange. The lithium ions are always attaching and detaching from the surface. So maybe I can't directly measure the lithium ions that are bound to the surface, but I can utilize the exchange between the two environments. Because they're always exchanging, the lithium ions are always exchanging between the two environments, it must have an effect on the NMR signal. So this is what I tried to achieve. By applying pulses at frequencies I suspect belong to the surface-bound lithium, I can kill their signal, basically making them invisible to the NMR measurement. So when the lithium ions detach from the surface and return to the solution, they reduce the intensity of the signal of the dissolved lithium ion. And as I get closer and closer to the peak of the dissolved lithium, the reduction will be greater and greater. By quantifying this reduction, I can finally see the elusive surface layer. We see it here in this measurement in the pink region, representing the surface-bound lithium, and the blue peak representing the original peak of the dissolved lithium ion. The pink peak is very broad because the surface is actually composed of many different chemical environments. So it's not just at one frequency. Now that we can see the elusive surface layer, we can finally start to understand its chemical and physical properties. We can study the ways lithium ions travel through it and how much energy that requires. We can even measure it inside a functional battery. And we can see how the surface layer evolves with each charge and discharge cycle. The more we learn about the SEI layer, the more we understand how it affects the performance of the battery, the closer we get to building better batteries for the future. I want to thank my mentor, Dr. Michal Eskes, and my entire group for their support and encouragement for coming here, which is not easy for me. So thank you.
Thank you, Shakked, for this nice talk. Questions?
You talk about getting the peak by means of observing peak change. Do you look into perhaps fractions that aren't exchangeable? Is there any way to test that?
If I had a peak and I would see that it was not participating, then yes. But because I only have these two peaks and I know they are in exchange, so I don't know of any other environments.
So can you follow the change in this invisible peak when the battery ages and becomes really not efficient in charging, discharging?
Yes, that's the goal, to follow different batteries, different stages of their life in different conditions and understand how the exchange changes.
Right.
So how do you think this knowledge will help us to gain better batteries?
Because if we can understand how, in different conditions, different surface layers form, and we can actually see which surface layers are helpful for us and which are detrimental to the battery, then we can decide, let's make this battery, which is better. We can actually see the impact.
Okay, so with that, I would like to thank Shakked. Good job. Thank you very much.